So I really liked the video that the Creel made about branchless programming. I enjoyed it so much that it inspired me to reproduce his steps in my own video for a learning exercise and for kind of to push this new compiler that I've been working on further to see if it can do these instructions, these advanced instructions. So what I have here is quite a module with multiple versions of least, a function I call least, which is a function that returns the least of value of two values, just like the Creel's video had, and then it's like 6 versions of UCase for uppercasing data, and the version 6 of UCase will be SIMD, and then we're going to do time tests, timing all these versions to see which one runs. First we're going to see which ones work. There's a few that don't work. And then we're going to do time tests and see of the working ones, which ones work the fastest. So it's going to be fun. I hope everybody enjoys it. It might, some people might not like tracing assembly code. I think if you actually kind of get into it, you might enjoy it. So without further ado, let's get rocking and rolling. Okay, we're going to be looking at a function called least1. It takes in a parameter A and a parameter B. The first line is a compare of A and B. The result of the comparison, if A is less than B, it's going to perform a jump here, and the jump will come down to this line, and then that will move A into the return register, RAX. If A is not less than or equal to B, then the jump will not happen, and that's where this line will execute, and this will move B into the return register, and then perform a return, which will be a function return to come back to the caller. What I'm going to do now is switch over to the debugger so we can take a look at this in real action to see what it looks like with the real lines of assembly. Okay, we're on line 1. Our RCX register has been pre-filled up with 1, and RDX has been pre-filled up with 2. That's our values A and B. They were passed into the function. So the first thing we do is compare A comma B. Notice here before the comparison, the sign flag is 0. Sign represents a -1. So this comparison is going to take 1 minus 2, and that's going to result in a negative number, and the sign flag will turn high. So let's do that. So that comparison happened, and you can see that that bit's high. It's saying that the result of the subtraction is a negative number. But the RCX and RDX registers were not changed. That's what the difference between a comparison and a subtraction are, is that the answer is not written anywhere. It just records properties of the answer in the flags register. So now this is a conditional jump. Jump less than or equal. It's going to be using these bits in the flags register to decide if it wants to jump. And when we execute that line, it does jump because the answer was less than or equal, because the sign flag is set high. Moves us down here where we're going to move the value of A, which is in the RCX register, into the return register, which is RAX. And the function will exit. Now, if B is greater than A, the jump wouldn't have happened. It would have come to this line, and then B would have been put into A. Okay, what we're going to do here now is take a look at a function called least3. The reason I skipped over least2 is because I couldn't get it to work, and least3 is just kind of a rewrite of least2 that I did get to work. So it takes in the same inputs A and B, but you might notice that the word leaf isn't here for the function. So it's not going to be a leaf function, which you'll see what impact that has on it when we get in the debugger. It won't be visible here from this screen. So the first thing we do is zero out the return register, REX. Now this is kind of in two halves here. Two compares, two set LE and a set G, and two IMOLs and two adds. So what it's going to be kind of doing is, and A is 1 and B is 2, so A is less than B in this case. So what it's going to do is it's going to do an equation of 1 times A, which is 1 times 1, plus 0 times 2, since B is 2. And 0 times anything makes 0, so you end up with the answer being 1, which is the correct answer for the least. So let's try to step through this in these lines of code, and then we'll go to the debugger, and it might be a little more clear in the debugger. Compare A and B. If A is less than B, set the AL byte high. Then go ahead and take and multiply that AL byte, it's in the full register that's zeroed out, times A. So that's going to be 1 times 1. Now add that result to subtotal. And subtotal is going to be, I think, R10. So now R10 will equal to 1. Now we go through and do a compare again. Compare A and B again. Set the AL byte high if the result was greater than. Well, in this case it's not greater than, so AL will be a 0. Multiply 0 times 2, and the answer will be 0. Add 0 plus the subtotal, and that will write into the REX register for the return. So let's go take a look at this in the debugger and step through it as well. Okay, first thing we're going to do is, on entering the function, is we're going to move the value of 1 and the value of 2 into the what's called the shadow space on the stack, and that's saving the values. And this is happening because it wasn't declared a leaf function. If you look down here, you're going to see this is my stack space down here that's got leftover date in it. And when we hit F, we step through this, you can see that a 1 is down there and then a 2 is down there, so those are saved on the stack. That's why this test isn't going to be very fair, and I didn't include this in the time test because of saving back and forth into memory is going to make it slower just from that alone. So here we go. We're going to clear out the REX register. We're going to compare, or we're going to move into RSA. I think it's A off the stack. So RSA now it's B, sorry. So move B, right, RDX, the 10, yeah, I should have seen that. So now we're going to compare A and B. We see our sign flag was set high, so we know it's a negative number. Set less than or equal, the AL byte is right here. If that sign flag is high, it's going to set that to a 1. Boom, it got set high. Now do a multiplication of AL times what's in memory, and that's going to be 1 times 1. And the answer is 1 again, so it doesn't look like it did anything. Now R10 was where we're accumulating the subtotal. We're going to add 1 into R10. There it is. Now we're going to do a compare again. So in RSI we have the value 2 again. And we're going to compare that in memory with basically 1 minus 2 is what it's going to do. 1 minus 2 happens again, and the sign flag is high again. Now we're going to do a set the AL register high if the result is greater than, which it was not. So that's going to turn into a 0, and I'm going to execute that line, and it did turn into a 0. Now we're going to multiply 2 times 0, and we're going to get 0. And now we're going to add 0 into 1, and we have 1, and that's our return. Okay, so there is the branchless version with no jumps. After getting least 3 to work, I decided to take a little break, and I went up to a pop machine downtown to get a soda. And I was standing there, and I was thinking about this, and I thought of a different way to do it that's still probably considered branchless. And that's what least 4 represents. So we're gonna trace through these 4 lines, then go to the debugger and watch them and watch how they run. Notice that this is a leaf function, so it won't be using the stack. It'll be using the RCX and RDX registers again for A and B. Let's start out. So clear out RAX, compare A and B. If the result of the comparison is less than 0, then move the value of A into the return register. Then you come right here, and if the value of the compare was greater than or equal to 0, move the value of B into the register. And that's it. So here's the code in the debugger. We're on the point in time where we're going to clear out the RAX register. And now we're going to do the compare of RCX and RDX, which is essentially 1 minus 2. That's set the sign flag high, the sign bit high. Now we're going to do a conditional move, less than. So if the sign bit is high, and it is, then it'll move the value of RCX into RAX. So it'll move 1 up to there, and it does. Now it's going to do a conditional move greater than or equal, which it's not greater than or equal, so it will not do the move. It will not be moving RDX up into the A. Will not be moving 2 into there. So we execute that line. And the result is sitting right where we need it to be to exit the function. And there it is. Simple and sweet. Okay, so I've jumped ahead a little bit in the program and have it set to the point where the timing of the 2 functions, least 1 and least 4, is going to happen. Let me drag my results window, or my DOS prompt, command prompt window in here to show you where we're at. What it's done so far is run each of the 4 functions, setting A equals 1 and B equals 2 in. You can see that 3 out of the 4 returned the proper value. Then I changed the value of A to 3 and ran all 4 functions again, and all 4 functions did return the proper value. So what I'm going to do is I'm going to run now a test on least 1 versus least 4. I got to drag this off the screen to be able to do that, but I'll drag it back. And There's the results of that. So least one with one jump was a hex number, 261 milliseconds in hex. And that's not for just one function run, that's for a ton of iterations. Least 4 then ran through the same test and did it in 223 milliseconds in hex. So it was faster, and you can do a calculation to figure how much faster, but the branchless jumps was faster in this case. It turns out, though, you have to write very small optimized code and to make it work. And that's that. So now we're done with the least function. We're now going to move into the portion of the video that deals with the uppercasing of string data. I'd like to start by looking at my first function I wrote called UCase1. This is going to do is take two parameters. One will be the address of some text, and the other parameter will be a buffer to write the results into, the address of a buffer to write results into. So I have an offset variable that's really a register. Again, that's going to be R10 when it runs. And what I'm going to do is I'm going to first subtract 1 from it outside of the loop to kind of set up an initial condition. And then inside, this indentation is inside of my loop. And this is the top of the loop. It's kind of like a do loop that will increment the offset. So now it's back to 0, which is going to set us to start at the start of the string. So each time this loop goes through, it's going to do one character at a time. So this line will take the address of some text, add on the offset, which is 0, and move the contents in memory, that's what the brackets mean, at that resulting address calculation into the AL register, which is our first character. Now we're going to kind of analyze that character to decide if we want to subtract from it, subtract 32 from it, which is how you convert a lowercase character in the uppercase in the ASCII table. So first, characters 97 through 122 are the lowercase characters. 97 is the lowercase a, and 122 is the lowercase z. Unfortunately, I'm using ASCII numbers. When we get in the debugger, it's going to be in hex, so sorry for the confusion. So let's compare our first byte with 97, which is lowercase a. Jump less than. So if it's less than a, then all that data less than a is going to be untouched by the upper lowercase program. It will jump these indented lines down to this line, which saves out the character into the return buffer at the same offset. But if the character is greater than 97, greater than or equal, then it's going to do another compare in the character to see if compare it with 122, which is lowercase z. Jump greater than. Alright, if it's greater than z, it's going to jump these lines and again write the output. But if it's less than 122, then it's going to less than or equal, sorry, it's going to not do the jump, and it's going to then subtract 32 from the character, which will convert it into uppercase, and then it's going to move that result into the output buffer. At the bottom of the loop here, it does a compare on the character, looking for the character 0. 0 means is our end of string marker. If jump not equal to, so if it's not a 0, it's going to do the jump. If it is a 0, it's going to exit the function. The jump will jump upwards and land right here on this line, which is the top of our loop, which will increment the offset by 1 and start over again. This will cycle through over and over again until it reaches a 0, and at that point it'll exit the loop. So let's go in to the debugger and take a look at this running and see what we have. Okay, here we are. I started this a little before the function, so you can see what happens when a leaf function gets called. What it does is it moves information or the parameters into the registers RDX and RCX. You'll see that RDX is an address and RCX is an address. RCX is our first parameter. This is our string that everybody's going to be working on. Hello world. That's a tab I shoved in there from assembly. I wonder what is going to happen. So, also what's interesting about a leaf function is that you see up here this subtract from RSP and add to RSP. That creates shadow space for the parameters. That will not be happening on a leaf function. There is no shadow space created for the parameters. So let's go in there. First, R10 is our offset. It's initialized to 0. Now we're going to subtract 1 from R10. There's what a -1 looks like in binary, using, I believe, what's called the 2's complement. Now we're at the top of our loop. We're going to now increment R10 by 1, and we're back to 0. So now we're going to take RCX plus R10. That's a pointer calculation. It's going to be that number plus 0, and whatever's in memory at that place, it's going to pull out 1 byte and put it into the AL register. And let's do that. There's our first character. Our debugger shows it as an H. That's the one we're going to work on. So let's compare that character with 61. 61's our hex equivalent to, I think it was 97, I think. Jump less than. That was less than. 48 was less than 61. And we know that because it's an uppercase character. So there'll be no conversion done on an uppercase character. What we're going to do is we're going to move that character to our output buffer. Which it doesn't show us in the debugger yet, but we'll just trust that it's there. Now let's compare AL to 0. It's not 0, so we will do the jump. We'll go back to the top of the loop. Let's increment our offset 1. Now let's pull out of memory the second character. There's there's E, lowercase e. So this will need to be uppercased. Let's compare that to 61. Let's compare 65 to 61. So it's like 65 minus 61 is what it's going to do. So that's a positive number. The sign flag was set to 0 because that means it's the sign flag is 1 if it's the sign bit is 1 if it's a negative number. Jump less than. Okay, it did not jump because it's not less than, so no jump. Now we're going to compare 65 to 7a. So it'd be 65 minus 7a, which will be a negative number. So our sign flag is set high. And now we have a conditional jump, jump greater than. Jump if it's greater than. Well, it wasn't greater than, so it didn't jump. Now is where we subtract 20, which is decimal 32, from AL. So 65 minus 20 is 45, so we've effectively turned a lowercase e into an uppercase e, and now we're going to save that into our output buffer. And still not writing it for us. Let's compare to 0. Not 0. Let's go a little faster here. Increment our offset to 2. Pull the next byte, which is an L. Do a comparison. No jump. Do a comparison. No jump. All the lowercase characters will not be jumping. Subtract 20. Turns it to uppercase. Write it to the output. There we go. So now the debugger decided to start writing these out. Now we're going to look, is 4C a 0? Nope. Let's jump. Let's increment our offset to 3. We're going to try and pull the third character out of memory. Third character is an L. Compare. No jump, because it's greater than A. No jump again. It's in the alphabet. And we're going to convert that to uppercase. We're going to save that to the output buffer. Now we're going to see, what's 4C minus 0? Jump if it's not equal, and it's not, so we jump. And now we're going to increment our offset again. I pull the next character. Now this is kind of a special character I put in here. This is, well, it's greater than 7a. It's actually past Z in the alphabet. So compare, take 7b minus 61, jump less than. Well, it does qualify there. It didn't jump away. But this is the one where it's now going to take 7b minus 7a, and that is a positive number. So it's not a negative number, and it's jump greater than. So now it is greater than. And now it's a special case where it jumped that subtraction. Character did not get changed. It made it through one logic step that didn't pass through the other. We're going to save that to output. There it is. Let's keep going. I'm going to go a little faster here. There's the O. There's the got change. Tell as I step through here, it is working on each character one at a time. I'm going to keep hitting the button, moving through here. You can see the offsets counting up as I go. There's the letter it's loading in. There's where it's reading from. There's where it's writing to. It's going to keep going until it pulls in a 0. Kind of getting off my screen here a little bit. Let's hold it down and go faster. going to happen? Alright, just go through there, happen. Just want to make sure we see that the very end is, boom, there's our 0. So we've got all this, all of them in. We're going to move the 0 to the output. At the very end, we compare, take 0 minus 0. When 0 minus 0 is 0, so the 0 flag has been set, bit has been set high. Now this jump will jump not equal. Since that bit's high, it won't jump. We've exited the loop. There we go. There's the default standard UCase function that I wrote using jumps. Okay, now the next version of the UCase function is a branchless version, and here it is on the screen. You'll notice that there are some similarities here. It has the same offset, I guess decremented and then incremented inside of the loop. The kickout is the same at the bottom, looking for the 0, the jump not equal. The reading of the input buffer into the AL register is the same. The writing of the AL byte back out to the output buffer is the same. So what's different is everything in the middle. You notice there's no jumps in there. It's branchless. I would also like to point out this variable trigger that I have. It's unused. I did not get it cleaned up and out of there before the video. It was, when I was putting this together, it was something I thought I needed and then didn't use. The offset has been declared as the 4th variable, so it will no longer be R10 any longer. I kind of wish I had that at the top and recompiled, but I didn't, so we'll just have to adjust a little bit. Other than that, it's very similar. And now, to trace through this, I kind of really like doing that in the debugger more, because it has that nice visual aid of seeing what's in the registers, and to me it just makes more sense. So I'm just gonna skip talking about this and go right to the debugger, and we'll just kind of watch it run. So over here again, it's right before the function call. That's where my stopper's at. We load up RCX and RDX with our strings. You notice that the input string is the same, and the output string I've turned it all into pound signs so that I can see that it's working. I don't want the output string to have the right answer, and then you don't know if it's actually working or not. So let's go in there, and here we go. We're going to set R12W to 20. 20 happens to be, W is a word. I think it's 2 bytes, I believe. And 20 is the amount we're going to be subtracting. So that's our subtraction amount. Our 13 gets set to 0. I believe that's our counter, our offset, I mean, sorry. Which in a way that's kind of our counter. So at the top of the loop, or before the loop, we decrement it, turns it to Fs, and then this is the top of our do loop here. You can see the debugger puts this nice red line up here to show that the jump goes up to there. It's the top of our do loop. We're going to increment it back, so R13 is 0 again, and that's our offset from the string address. And we're going to clear out R10, clear out the last 2 bytes of the A register. We're going to load in our first character, and you see it here at the top. H has been loaded in. It's character 48. We're going to do a couple more clears. We're going to clear out our 11W. We're going to clear out our 8. And I went one step too fast. I went past the compare. What I did is it did a compare. It took 48 minus 61. So that's a negative number. So the sign flag bit has been set high. This is a instruction called set greater than or equal to R8B. So it's going to set that high or to a 1 if the flag's register is greater than or equal to, which it's not. So R8B does not get set. It stays at 0. Now we're going to take whatever's in R8D and shift it left 8 bits. So we're going to move that byte from there to there. It's kind of a bad example. You can't see a 0 shift to a 0, but we will the next iteration. Now we're going to compare AL to 7A, which is going to be 48 minus 7A. Again, that's a negative number. This time we're doing, so it is less than 7A, and H is less than Z. Now set less than or equal to. So the last one didn't set, but this is kind of an opposite one. Set less than or equal to R8B. That one sets that to a 1 because it was less than or equal to. Now what we're going to do is we're going to compare the R8D, which is these last 2 bytes, to 101. It's kind of like an and. Is it this and this? And it's not the same. It was actually what we're looking for is if it's equal or not. I'm not going to think about if it's greater than or less than. The 0 flag is 0, which means it's not equal. This is a conditional move equals R11W, R12W. So it's going to move what's in R12W into R11W if it's equal. And it wasn't, so it didn't move. Now we're going to subtract from the character 48 nothing, which is 0, and it doesn't change it. So essentially it does not change that character because it's already uppercase. Now we're going to move that to the output. There's our H, got moved. Alright, so do we have a 0? Nope. Let's jump to the top of the loop. Let's increment our 13 to 1. Now we're going to look at, that's our offset from the address of the string. Let's clear a couple of registers. Let's load in our next character. Now we have a lowercase e. This will need to be uppercased. Let's clear a couple registers. Let's compare 65 minus 61. 65 minus 61. It's not 0, it's not negative, it's just a basic positive number. This is the set greater than or equal to. Well, it's greater than. R8B, boom, got set to a 1. Now we're going to shift left that 1, 8 bits. Here's where you actually see a shift left happen. Boink. It's got shifted left 8 bits. Now we're going to compare our character 65 with lowercase z, so 65 minus 7a, and that is a negative number. There's our sign bit. Now set less than or equal to. Well, it's less than, so we're going to set R8B, the byte, sorry, to 1. There's 101. Now we're going to, so it was both greater than equal to 61 and less than or equal to 7a, and there's our kind of makeshift and we're going to say now compare 101 with 101, and voila, our 0 flag bit is set high, which means 101 subtraction is 0, which means they are equal, and the compare move equal, that will move what's in R12W, which is 20, or it's our subtraction quantity, into R11W. It moved it because they were equal. So now we can do the subtraction. Let's subtract from AX 65 minus 20. There's 45, and you can see that the lowercase e turned into an uppercase e. And now let's move that to the output. Voila. There's the branchless version. I can go faster. You can slow your video down if you want and kind of watch as it goes. I can even go faster yet. And you can see it constructing that output buffer as it goes. Uppercasing the characters that need to be uppercased and not touching the characters that aren't in the range. And it works. Okay, let's move on here to UCase 3. UCase 3 does a lookup into a data table, and it's a very simple data table. It's just 256 bytes, and at each byte location is written the answer of what a UCase character is, and that's run with an initialization function that will populate that. It's right here if you're curious. This runs on startup, runs through the logic, populates the buffer, and let's center that back. Okay, so it's actually very similar to what we've already been doing. It's a matter of having an offset, move reading a byte in, then do a lookup from the table, and then write the byte out, and then the bottom of the loop looks for a 0 to exit the loop. So let's go over and watch this run in the debugger. Okay, here's the call of the function. It's going to load the two buffers in. There's what we want up and lower, and there's the right buffer that's been all filled up with pound signs. Okay, so R10 is our offset again, or back to R10 we should say. R11, oh yeah, that's the address of the buffer. Let's take a look at that for a second. So that's 16268. Let's go here to the memory map, and there's our program. It starts at 12. Let's go down to 16268. So here you see the buffer starts right there, and you can see the characters in there. There's no lowercase characters. They've been changed to uppercase. And that's 256 bytes wide. You'll also notice down here is another buffer that is going to be used in UCase 4, and that it starts exactly on a 16-byte boundary. It's been aligned, and that's what the difference is between UCase 3 and UCase 4, is that the lookup data is 16-byte aligned. So let's find out where we were again. There we go. Hit F8, it'll take you there. And let's set our screen back. Okay, so R11 is the address of our lookup data. So we're going to decrement, subtract 1 from R10, fills up with F's. There's our start of our loop. Add 1 back to R10. Now we're at 0 again. Now we're going to move into the A byte, the first letter of the stream. And at this point in time, in one line of code, we're going to look up in our data table the R11 is the address of our data table, adding on the offset of our character, and pull in whatever byte is there, and it's the same uppercase character. Now we're going to write that byte out, see if it's 0, jump in our loop. So it is quicker. As you can tell, these, I don't know if I did that too fast or not, or maybe too slow, I don't know, but here is, again, it's the same thing. All these versions have 1 byte per iteration of the loop. So that's UCase 3. UCase 4 is the same exact thing, but it uses 16 byte aligned. And let's continue on to the next. Okay, now we're on to UCase 5. This is a version that does not work, by the way. We're going to look through it. It seemed like a good idea, but it doesn't work. It doesn't mean it can't work. There's something here, but this version as is does not work. What it essentially does is tries to turn off the bit that has the value 32 to it. And that's with this AND right here. Otherwise, the rest of this loop is the same as before. Also, I'd like you to notice this is a leaf function, so it's not going to have a stack, but it also has a local variable declared here that's not a register. It's going to be a stack variable. So it's called some lost variable. What this represents is, you know, when you're coding, a lot of times you have a variable that you have declared, but then you have no code for. So I was testing this tab over here called unused, and the unused tab will find a variable and then take you to it with a little link to help you find variables that are declared but not used. Likewise, I have a function called test else. I was testing my else that is no longer being called. These others they're actually being called. They're just not being called with the invoke statement. They're being called as a parameter to a function. So I guess it's not a foolproof system here. So let's go to the debugger and watch this run. Okay, so we see inside here there's a subtract to the RSP. That's because of that local variable that got declared. Then we're going to move 20 to the R10B register. 0 to 11. 0 is our offset. Here, let's get the stepping going. We're going to move 0 to RSI. Okay, what that's doing is that's actually initializing our variable that we don't like to 0 and sticking it on the stack. So you can see all these extra lines of code that are in there just because of that variable that got thrown in there. All that would be overhead that would slow things down a little bit. Not R10B. Okay, so okay, not into R10B. That's that inverted. That's that inversion I was talking about, where it's all the bits set opposite except for the 1 bit. The bit that has 32 value to it. So let's just do this. Here we go. We move H in there. We're going to AND H with R10B, which essentially will subtract. Well, it didn't subtract 32 to it because the bit was already low. That's kind of the tricky to it here. Just because you're making a bit low doesn't mean you're subtracting 32 to it. the bit may have already been low. So let me save it out, and there's our top of our loop. Let's go to this one. So 65, we know that one is going to be changed. That one effectively got that bit changed, and it uppercased it. So it looks like it's working here. Alright, I'm going to go a little few more. I'm going to show you where the problem is. It got to that one. It does O. And then it does the last bracket. So you notice it did change the brackets. So a lot of those special characters could become different, which isn't so good. And then here's the character that really is the kicker. Character 20 is the space. That's a decimal 32. Well, that is going to be affected by this and. It turned it into a 0. And it writes it out, which we know what happens when we have a 0, our loop exits. So the string, the output string, is only one word now. We effectively found a nice way to parse out words. So that's kind of it. I just stopped there. Like I said, there's kind of something there. I don't know, but that's it. It was kind of an idea. I threw it together. There it is. I put it in the video. It's something that works, but doesn't work good enough. I'm going to drag the screen over here now. I'm going to drag it back off. What I want to do is step a few more steps here. I can't have both screens on at the same time. And let's see what this looks like here. Okay, so this is a screen that I haven't been showing you very much. These are all tests of each UCase to see if they work. And it wraps, but it shows you the string to start with, and then it shows you the string that it ends up with. And that's UCase 1 works, UCase 2 works, UCase 3 works, UCase 4 works, UCase 5 ends up shortcutting, only doing one word, changing the curly brackets to the square brackets, and exits. So UCase 5 is not working. And that's UCase 5. There we go. Okay, now it's time for the final one, UCase 6. This is the one that does SIMD, single instruction, multiple data processing. This is the one that's supposed to go a lot faster, and it does, by the way. We'll see that later. So all right, so our loop here, our do loop, is very similar to how it was before, but the offset gets incremented by 10, and 10 in hex is 16 in decimal. So every time this loop runs, it processes 16 bytes, and versus every other one of these that was created, it was 1 byte processed per loop iteration. So that is essentially the #1 reason why this thing is going to run a lot faster, because it's doing more work per loop iteration. So these instructions look like complicated license plates that you're trying to figure out when you're behind somebody at a stoplight. They can be intimidating, but actually this is all very sensible when we watch it in the debugger, and that's where I'm going to do the tracings in the debugger, because it just seems a lot easier to watch the data flow. And let's just go over there then. Okay, so I've already executed a few steps here. What I want to do is, here's our register window. I'm going to drag this down. There's a lot more registers available than what we've been using. Here's a set of registers that also exists. These are 16-byte registers. Below them are more registers, but we won't be using those today. So, first thing we're going to do, we've already got R10 set up to be subtracted 10 from it. We're still outside of our do loop. We're going to do a little initialization here and load in a few buffers. So this one here, I actually forget exactly what it is. Compare equal D, same register, same register. Essentially it turned everything to F. Sorry, I don't exactly remember what that instruction means. Let's go to the next one. This is the move DQU. This is where we're going to move a buffer, some buffer data into XMM1. So let's watch XMM1. There's all our 60s. Okay, 60s. We know that's lowercase a. Let's do another buffer. Let's load in XMM2. There's all our 7As. That's our lowercase z. And the last one we're going to load in is XMM3. There's all our 20s. That's the value we subtract to convert a character. So now we're, as you can tell from our red line here, we're now entering our do loop, and now we're going to increment our 10 by 10. That'll make it 0 again, and that's up here. There's our 10 at 0. Go back down here. And so let's start off with moving some data into XMM4. That right there is our data input stream. And I believe it's backwards. So this is our capital H here. Now what we're going to do is we're going to copy what's in XMM4 into XMM5. So we just made another copy of it. And then we're going to do another move into 6. Now we have 3 copies of our input stream. Okay, so now P, I believe P means packed. Packed, compare, greater than byte. XMM5, XMM1. So we're going to compare each byte of 5 with 1. And if it's greater than, then it sets the bits high in XMM5. So let's kind of look at that. So 2, 3, and 4 are the same, or 4 is the same data. So like 65 compared to 60, it's greater than. So it gets set high. So if XMM5 is greater than XMM1, then set all the bits high. So 60 compared to 48, 48 is not greater than 60, so it did not get set high. 6C, well, basically you can tell that the 20s is low. Pretty much all the characters that you want to that are above 60. Let's just say that because I can't say all. Let's continue. So packed, compare, greater than byte again, and we're going to go in XMM6. We're going to change XMM6. We're going to have it compared to XMM2. Now that's our 7A, which is our lowercase z. So we run that. We end up getting the bits set high whenever these numbers are greater than 7A. So 7D was greater than 7A, so those got set high. 7B was greater than 7A, so those bits got set high. And I purposely put, those happen to be our curly braces, I purposely put those in there just so that would happen, or else it was all zeros. Okay, so now let's do a packed. I believe P means packed, and packed meaning that It's kind of a prefix meaning an array of values. Anyway, XOR. We're going to do an XOR on XMEM6 with XMEM0. What that does is it's going to invert it for us. So we don't have a NOT available to us, but we've used a little trick here to create a register full of Fs, and we XORed it, and it ended up kind of knotting everything. So what that means is all the Fs represent, we're not interested in stuff that's greater than 7a. We want stuff that's less than or equal to 7a. So we wanted to invert that. So all the Fs represent something that needs to be changed, needs to be uppercased. And then XMEM5 represents things that need to be uppercased too. But it's like two halves to a picture. And we're going to need to put that picture together. And that's what we're going to do next. So let's move 5 into 7. Okay, the only reason I did that is it's probably a little unnecessary, just to make things easier. Kind of give us something to look at. Since we've got plenty of registers to play with here. So we just made a copy of 5 to 7. So now we're going to do an AND on 7 and 6. All right, so we're basically going to AND these two together. And that's that. So now you can look at 5, 6, and 7 together as a whole. And you can see that 5 and 6 were ANDed together to create 7. So like zeros there and F's there created zeros here. It has to have F's in both of them to run it down. And so the F's all represent bytes that need to be uppercased or need to have 32 subtracted from them. So now let's move 7 into 8. We're just going to copy it down because we're going to work on it a little bit here. And we're going to do an XOR on 8, which is going to reverse everything. So now 8 represents everything that we want to not work on or don't touch. So now we've got these masks we're building. Let's just keep continuing. So let's copy our input data stream to XMM10. All right, so there we go. There's our input stream again. We just copied her down, and we're not going to use 9. I just put a space in there to kind of separate things out because we got plenty to work with. Now let's AND 10 and 8 together. So if we AND 10 and 8 together, we end up with the characters that we don't want to touch, and zeros for the ones we do want to touch. Again, half the picture. Now let's move 4 into 15. So there's a copy of our input data. Move down to 15. So 15 is, I skipped those because 15 is our final one. So I'm just jumping down to the bottom there that we're going to work with. So what we're going to do on 15 is we're going to do a subtract from 3, or 3 from it. So that's subtract 20 from every character. So now that's going to do every single character, which is not technically right. So we've got some characters that should not have been subtracted from, right? So we're going to try to fix that. So if we AND 7 and 15 together, 7 represents our mask of the characters that needed to be changed. So we AND those two together, we see that characters we weren't supposed to change all turn to zeros. All right, so we're getting closer. Now if we OR 15 and 10 together, because we have two halves of the picture here, we can OR these two together, and in one more step right there, we have our final answer in XMEM15, and then we're going to just move every one of those bytes into memory with our little memory calculation. And here's an instruction I looked up. thought it was interesting. It's a way to strip a byte off of an XMM register, and we want to look for a 0 on the 15th or 16th byte, no matter how you number them. The last byte, we'll say. We're gonna strip that out, and ironically, it looks like it's a 4-byte register, but it's putting 1 byte in it. So I guess whatever have you. So 46, I believe, should be in the A register. There it is. 46 got pulled out, and I believe it's 0 the other bytes. I'm not worried about it. So then that's our kick out. We're going to look and see if A is 0. If it's not 0, we're going to go back through the loop. We're going to do it again. We'll do it a little faster this time. You can slow down the video and watch it. And there's our answer. Strip the byte. Looks like we're not done yet. There's 2 iterations. Let's go through. Might be a 3rd one here. Looks like it might be done now. Oh, we're not. Let's go again. And do I type that many characters in? And we're done. Okay. Let's go out. Let's step through that. Let's drag this window over here. And there's all 6 of our examples. All this was is to prove that the functions work. We've proved that function 5 does not work, but function 6 is a working function because it has the same answers as the other ones. It looks good. It was done using the SIMD instructions. So now comes to the fun part. We're going to run time tests on each of these functions and see which one's faster. Oh, here we go. Okay, so this is the point in the video where the time tests are going to run. I'm not going to trace through my code for creating the iterations and timing the loops. So I'm just going to run that, and we can watch and see what happens. So let's go full speed, let this program run. You can see that UCase 1 just ran, UCase 2, 3, 4, 5, 6. You notice at the end that 5 and 6 were a lot quicker than the beginning ones. So UCase 1 is a hex B55 milliseconds. UCase 2 is branchless AD9. Okay, it was a little quicker this time. It seems to have different results every time. It's not always that much quicker, but it's usually a little quicker. The DB lookup seems to be a lot faster. So that was a good solution. The align DB lookup was even a little faster than that. And that kind of holds the same every time. The alignment does seem to get you an increase, which you can probably say that that's not a little bit. That might be maybe a lot. Depends on what your version of a little and lot is. Now the XOR is one we need to throw out because it doesn't even do it right. I shouldn't even ran that one. But the SIMD is the main one that does work, and it ran fast. 9C milliseconds versus, let's say, B55. I think if you were to get out your calculator and do the math, I think you'll find it's maybe 15 to 20 times faster, which is just plain cool and plain amazing. I'd like to thank the Creel for introducing this whole topic. I'm really glad I got a chance to step through and put the code together. I learned a lot. I've been building this compiler for all these years, but I've been so stuck in just trying to get the basics to work and all the variations of the basic move to work that I never really had a chance to play with any of these extended instructions. And so now I've had the chance to do some conditional moves, some set less than, greater than, those sets. Now I've had a chance to do the XMM registers. Yes, and by the way, the compiler throughout this process had lots of bugs in it, and I was fixing different things to make it do these things. So it was kind of a project for me getting all this to work. And then I never even knew what this was about or how this worked. This SIMD. Now I had a chance to watch it and see how it works, and it's very cool. It really is very cool. From here, I don't, applying it to different situations. That's something, that's the next question. But this is kind of a lot for this video, and this is kind of a good stopping point for me. So if anybody's made it this far, I'd like to thank you for being here, and I hope you enjoyed it. And if you'd like to give me a like and a subscribe, I do plan on making more assembly related videos in the future here. So I'd like an audience if I could. So thanks.